Welcome to AI Paper Podcasts. We break down the latest research so you don't have to. Today, we're tackling a really significant paper, the unreasonable effectiveness of scaling agents for computer use. And our mission here is to figure out how they're fixing or trying to fix the fragility problem with computer use agents, CUAs.
That's the big one, isn't it? Anyone building these knows the pain. CUAs are meant for complex digital tasks, but they're just so unreliable. High variance is the killer.
Right, one run works perfectly over, say, 100 steps. The next run just crashes and burns because of one tiny mistake early on. These small errors just pile up.
Exactly, and that's especially true for these long horizon tasks. So the paper introduces something called behavior best of n, or bBoN.
Okay, so what's the core idea there?
Well, it's a wide scaling approach. They run multiple attempts, multiple rollouts in parallel. But the key isn't just running more attempts.
It's how they pick the best one, right?
Precisely. They use what they call behavior narratives, basically, structured summaries of what the agent did to reliably choose the best complete trajectory. It's about understanding the behavior, not just the outcome.
And results.
Pretty impressive. They hit a new state-of-the-art on OSWorld. That's a tough benchmark. 69.9% success rate over 100 steps.
Wow, okay. What was the previous best?
COACT 1 was at 59.9%, and maybe more importantly, human performance is around 72%, so they're getting really close.
Okay, so the big takeaway for everyone listening, especially if you're working on agents.
Scaling works, yes, but only if you pair it with this kind of structured trajectory understanding and a principled way to select the best run. It's the selection mechanism that unlocks the performance.
Right, it's not just throwing more compute at it blindly.
Definitely not.
All right, let's dig deeper. Section 1. The reliability challenge. Why are these CUAs so fragile in the first place? We know it's hard, but what are the specific factors?
Well, you mentioned the accumulated mistakes. That's huge. But there's also delayed feedback that the agent does something, and the consequence isn't obvious for many steps.
Yeah, and the solution paths can branch out like crazy. There are often many ways to do something on a computer.
Exactly. Plus, you've got all the environmental noise things like unexpected pop-ups, slate UI changes between sessions, even just network latency can throw things off.
It all adds up to this high variance problem. An agent might look great on one run and then just fail catastrophically the next 5 times.
Which naturally leads you to think about wide scaling. If one agent path fails, maybe another one running in parallel will find a way through.
And the paper mentions this idea of disjoint task success, right? Like different agents might succeed on different types of problems within the benchmark.
Yeah, exactly. Figure 2 in the paper shows this nicely. Agent A might solve tasks 1 to 5, Agent B solves 4-8. If you run both, you cover tasks 1 through 8. That's the intuition.
But scaling CUAs isn't as simple as scaling, say, game agents. There are unique hurdles here.
Oh, definitely. First, the trajectories themselves are incredibly dense. You've got screenshots, sometimes videos, the specific actions taken, XY coordinates. It's a lot of multimodal data.
How do you even process all that efficiently?
That's a major challenge. And then there's evaluation. Many computer tasks don't have just one single correct final state. You could achieve the goal in multiple ways.
So a simple check at the end isn't enough.
Often, no. You need to understand the process. Did the agent achieve the goal efficiently and correctly? This makes automatic evaluation really tricky.
So effective scaling needs new methods. You need to represent these long trajectories compactly, and you need to evaluate them reliably.
Correct. And this is where bBoN really differs from prior work. They specifically contrast their approach, which is trajectory level best of n, with older methods like stepwise best of n.
Okay, what's the difference there? Stepwise sounds like you make a decision at each step based on multiple short-term predictions.
Exactly. Imagine you're deciding on the next click. Stepwise bBoN might look at 5 possible clicks, predict which one seems best right now, and commit the agent to that action.
But that might lead you down a garden path, right? A choice that looks good locally could be terrible globally.
Precisely. You commit the rollout to that single path based on very limited look ahead. If a different early choice would have opened up a much easier path later, stepwise bBoN misses it.
Whereas bBoN runs, say, end-to-end complete, independent trajectories from start to finish.
Yes, full rollouts. Then after they're all done, it looks at all 10 complete attempts and selects the best overall finished product.
That sounds much more robust. It allows for exploring different strategies entirely.
It is. It lets the agents try diverse approaches in the early stages without being penalized for a locally suboptimal step that might lead to a globally better solution. It's fundamentally a different system architecture.
Okay, let's get into the mechanics of bBoN. There are two main components, the behavior narrative generator and the behavior best of n judge.
Right. So first, the narrative generator. Its job is to tackle that information density problem we talked about.
Taking the raw trajectory, screenshots, actions, and making it manageable.
Exactly. It distills it down into a concise behavior narrative. Think of it as a summary that captures the task-relevant action effects steps, filtering out all the irrelevant visual detail.
How does it do that? Using a VLM.
Yep. A visual language model processes transitions specifically, the screenshot before the action itself, and the screenshot after the action to generate these little summaries, which they call facts, or phi.
VLMs can hallucinate, right? How do they make sure these facts are accurate?
This is a really clever bit. They use specific visual augmentations before feeding the images to the VLM.
Like what?
Okay, so for a click action, they overlay a marker, like a red circle, on the before screenshot right where the agent is about to click.
So the VLM knows exactly how the action occurred.
Right. And then on the after screenshot, they extract a zoomed-in crop, a small square centered right on the pointer coordinate where the click happened, and they outline that region.
I see. So the VLM gets the context of the click location and a high-resolution view of the immediate result of the click.
Precisely. It helps the VLM verify the effect of the action. Did clicking that button actually close the dialogue? The zoomed crop provides the fine-grained visual evidence. They also keep the very first and very last screenshots to ground the whole narrative.
That sounds really smart. Was there any worry, though, that adding those markers or crops might, I don't know, make it too easy for the VLM or introduce some bias?
That's a fair question. I think the paper implicitly answers it by showing how much standard VLMs struggle without these aids. The visual details in GUIs are often subtle.
Right.
So this coaching, as you put it, seems necessary to make the VLM a reliable auditor of the agent's behavior. Trying to infer action effects just from raw, unannotated screenshots proved much less effective. The transition-focused approach with augmentation is key.
Okay, so we had these verified behavior narratives for each of the N rollouts. Now the behavior best of N judge steps in.
Yep. Its role is straightforward. Compare all these narratives and pick the best one.
And how does it compare them? Pairwise comparisons. Like a tournament.
They actually opted for something more efficient. They use a single-round multiple-choice question, an MCQ format.
So the judge sees all, say, 10 narratives at once. He just picks the winner.
Exactly. It gets the task description and all the candidate narratives simultaneously and has to choose the index of the best one.
That sounds way faster. Pairwise could get computationally expensive, especially for large N.
For sure. They mention it's roughly constant time, O1 for selection versus potentially ON, or more for iterative methods, and the token cost scales linearly with N, not quadratically.
Which is huge if you're paying for LLM inference.
Absolutely. And they found this MCQ approach worked just as well as pairwise for the N values they tested, like N2 up to N5, while being much more efficient.
Did they find anything special about how they prompted the judge?
Yeah, a small but interesting detail. They gave it a system prompt that explicitly told it to cite and contrast facts from the narratives to justify its choice.
So forcing it to ground its decision in the evidence provided.
Right. And they found this actually gave a small performance bump, maybe around 1%. It suggests making the judge reason step by step over the provided behavior summaries improves the final selection quality.
Okay, but even the best judge needs good options to choose from. This whole system relies on getting decent rollouts in the first place. Let's talk about the base agent they used, Agent S3.
Right. Agent S3 is the foundation here. It's an improved version of their previous Agent S2 framework. They made some key design choices to boost its capability and efficiency even before applying bBoN.
What were the main changes?
Two big ones. First, they integrated a coding agent directly into the GUI agent's action space.
Meaning the agent can decide whether to click around or just write some code to get the job done.
Pretty much, yeah. If a task involves, say, bulk edits or parsing structured data, the GUI policy can decide to invoke the coding agent to handle it programmatically, which is often way more efficient than clicking 50 times.
That makes sense. What was the second change?
They switched to a flat policy, getting rid of hierarchical planning.
Why drop the hierarchy? Isn't planning good?
Well, their reasoning was that modern foundation models, like the GPT-4 or GPT-5 class models they used, are pretty good at holding short-term plans in context anyway.
So a separate high-level planner might just add complexity or latency?
Or even introduce errors, like sticking to an outdated sub-goal when the screen has clearly changed. A flat policy that can replan at any step based on the current observation turned out to be more agile and effective.
And did this Agent S3 baseline actually perform better?
Significantly better, and more efficiently too. Table 2 shows the comparison with Agent S2 using GPT-5. S3 got a 13.8% higher success rate.
Okay, that's solid.
But get this, it achieved that while using 52.3% fewer LLM calls. And it finished tasks 62.4% faster on average.
So better, cheaper, and faster. That's a strong baseline.
Absolutely. It makes the whole approach much more practical. You're not just getting accuracy gains by burning tons more compute at the base level.
And then taking this efficient Agent S3 and applying bBoN with end-to-end rollouts is what pushed the final success rate up to that 69.9% on OSWorld.
That's the number. It represents another 7.3% absolute gain on top of the already improved S3 baseline. That's where the unreasonable effectiveness really shows up. The scaling, combined with smart selection, adds substantial performance.
Let's look closer at that scaling effect. Figure 4 in the paper plots performance against N, the number of rollouts.
Yeah, it pretty much confirms the intuition. Generally, as you increase N, the success rate goes up. And importantly, this holds true for both the big model, GPT-5, and the smaller one they tested, GPT-5 Mini.
So wide scaling benefits models across the capability spectrum. Although I noticed GPT-5 had a tiny dip at N6. Any idea why?
They don't explicitly say. Could be just noise in the evaluation or maybe some subtle interaction with the judge at that specific N. But the overall trend is clearly positive.
The paper also looked at mixing different models for the rollouts, right? Like instead of 10 runs of GPT-5, maybe run 5 of GPT-5 and 5 of Gemini 2.5 Pro.
Yes, the ensemble selection part. Table 3 explores this. They found that mixing models generally increased the coverage, the chance that at least one agent succeeded. The most diverse mix, all models, got the highest coverage at 75.4%.
The coverage isn't the same as the final success rate after the judge makes its pick.
Right. The highest final success rate after bBoN selection actually came from mixing just 2 top models, GPT-5 and Gemini 2.5 Pro. That combination hit 66.7% success and also had very high coverage, 78.0%.
Interesting. So the takeaway is maybe mixed diverse, but also highly capable models for the best overall result. It's not just about maximum variety, but quality variety.
That seems to be the implication. You're combining models that are both strong, but likely have different strengths and failure modes.
And what about the narratives themselves? Did they prove those summaries were actually better than just giving the judge raw screenshots?
Absolutely crucial. They did an ablation study on this, Table 4. Using the behavior narratives gave a 3.4% absolute improvement in success rate compared to the best baseline that tried to use just screenshots or other representations.
So trying to understand the trajectory just by looking at a sequence of images is too hard.
It seems so. The concise action effect summaries provided by the narratives are necessary for the judge to reliably figure out what happened and which run was best. Generating facts over transitions was key.
And one more validation. The selection mechanism. They compared bBoN's comparative MCQ approach to just ranking each trajectory independently, sort of like adapting WebJudge.
Right. Figure 5 shows this clearly. The independent ranking approach gave very little benefit. Its performance plateaued quickly, not much better than just picking a random rollout.
Why do you think that is?
It really highlights that for these complex multi-step tasks, judging a trajectory in isolation is just not effective enough. You need to compare them against each other to see the relative merits, the subtle differences in efficiency or correctness. The comparative nature of bBoN is essential.
Okay, makes sense. How well did this whole system generalize? Did it work outside of the main OSWorld benchmark?
Yeah, they tested it on other environments too. Using just N3 rollouts, bBoN still provided decent gains over the Agent S3 baseline.
Like there.
On WindowsAgentArena, it gave a 6.4% improvement, and on AndroidWorld, a 3.5% improvement.
So the core idea generating narratives and comparing them seems robust across different operating systems and UI styles.
It appears so. The structured auditing and selection process isn't tied to one specific OS look and feel.
Now, there was an interesting point about judge accuracy versus the benchmark itself.
Yes, really important for anyone developing or using these benchmarks. The automated scripts for OSWorld suggested the bBoN judge was only about 78.4% accurate on the subset of tasks where its choice actually mattered.
But when humans looked at those same cases?
Human evaluation found the judge was actually making the correct selection over 92% of the time.
That's a huge difference. What does that imply?
It strongly suggests the benchmark evaluation scripts themselves are imperfect. They're often too rigid, only accepting one specific, predefined solution path.
So the agent might find a perfectly valid, maybe even better way to accomplish the task, but the script marks it as a failure because it wasn't the expected way.
Exactly. It's a common problem in complex task evaluation, and it means the reported 69.9% might even be understating the agent's true capabilities slightly.
Okay, let's talk about where it did fail. Even with bBoN, it didn't solve everything. There were 12 problems left. What went wrong there?
The failures basically fell into two main buckets. The bigger bucket, with 8 cases, was due to hallucinations or errors in the behavior narrative generator itself.
So the VLM making mistakes when summarizing the trajectory.
Yeah. Even with the visual augmentations, sometimes it missed subtle but critical details. The example they give is the VLM failing to notice a negative sign on a number in a text box. Small visual detail, huge semantic impact.
Ouch. Okay, what was the other failure category?
The other 4 failures were these really interesting Code-GUI handoff problems.
This relates back to Agent S3 having both coding and GUI actions.
Exactly. What happened was the coding agent would be invoked and successfully make a change programmatically, like editing a file correctly.
Okay, good.
But then the main GUI agent policy would fail to recognize that the coding agent had already succeeded. So it would proceed with its own plan and perform GUI actions that actually undid or overwrote the correct changes made by the code.
Oh no, so the agents weren't coordinating properly.
Right. It's a failure in understanding the shared state or recognizing the successful outcome of the delegated coding task. And because the judge sees the final state after the erroneous GUI actions, it might incorrectly favor that flawed trajectory.
That's a tricky interaction. It's not just about fixing individual errors, but managing the interplay between different agent capabilities.
Precisely. It points to the need for better state cracking and communication between different components or modes of the agent.
And finally, we have to talk about the big limitation, the elephant in the room for real-world deployment.
Yeah, the paper is very upfront about this. The entire bBoN framework and the impressive results rely heavily on having access to a controlled environment, typically a virtual machine.
Why is the VM so critical?
Because it allows for perfectly repeatable initializations. Every single one of the end rollouts starts from the exact same clean state. This guarantees the rollouts are truly independent.
But in the real world, agents won't run in pristine VMs. They'll run on a user's messy desktop or interact with shared online services.
Exactly. The moment you have agents interacting with things like a shared Amazon shopping cart, or editing the same Google Doc, or even just dealing with files on a normal OS, you introduce the possibility of cross-run interference.
One agent's actions could mess up the starting state for another agent running concurrently or shortly after.
Right. Agent A adds item X to the cart, then Agent B starts its run and sees item X already there, completely changing its required actions. This breaks the independence assumption that bBoN relies on.
So tackling this cross-run interference in shared dynamic environments is the next major hurdle.
It seems to be. They've shown near human-level performance is possible in a controlled setting, but making it work reliably in the wild with shared resources is a whole different challenge.
Okay, let's wrap this up. To summarize, this paper argues that the unreasonable effectiveness comes not just from scaling, but from scaling smartly.
Right. The bBoN framework, with its behavior narratives generated via augmented VLM analysis and the comparative MCQ judge, provides the necessary structured quality control.
It allows the system to reliably identify the best path among many parallel attempts, pushing CUA performance close to human levels on complex, long-horizon tasks in controlled environments.
And the key insight for people building these systems is that the architecture matters immensely. It's not just about having the single best base agent. It's about having a robust system for generating diversity and selecting the best outcome.
So for our listeners, the provocative thought to chew on is this. Given that bBoN's success hinges on that controlled VM environment, ensuring independent rollouts, how could we design a trajectory selection mechanism, maybe an evolution of bBoN, that can actually handle or perhaps even leverage the reality of cross-run interference when agents are deployed in the messy, shared, volatile online world?
That's the multi-million-dollar question, isn't it? How do you select the best trajectory when the trajectories themselves might be stepping on each other's toes?
Something for everyone to think about. Thanks for tuning into AI Paper Podcasts.